Hi, welcome to my talk. My name is Chris Zhang, and I'm a PhD student from UC Santa Barbara. I'm glad to present our work, Optimistic Concurrency Control for Real-World Go programs. This work is collaborated with Milind Chabbi and Adam Welc from Uber, and my advisor, Tim Sherwood from UC Santa Barbara. Go is a modern programming language which has similarities with C, and it's becoming more and more popular recently. One key features for Go is Go supports concurrency by its core. If we prefix a Go keyword with any function calls, those calls can be executed concurrently. And the concurrent function is implemented using Go routine. It's kind of like the lightweight thread model. Fundamentally, Go has two concurrency control models. First is shared memory using Mutex lock, and the second one is message passing using channel. For this work, we will focus on the shared memory, which is Mutex lock-based concurrency control. All right, Mutex lock is a way of pessimistic concurrency control because lock preemptively serialize Go routines, regardless of the shared variables. And this mechanism sometimes could be very expensive. Based on the profiles, we observe 5 to 30% overhead in production code. On the right is an example Go code how to use Mutex locks. First, we call the lock to acquire the lock. Then we do the job in the critical section. And after that, we call unlock to release the lock. All right. Do we really need to be pessimistic if the conflicts are rare? And the answer is probably not. We have an optimistic concurrency control transactional memory. The TM speculatively executes concurrent regions, assuming no conflicting shared memory access will happen. However, if such conflict does happen, the TM will be aborted and retried. And the TM is well suited for boosting performance of otherwise lock-protected critical section for a long time. And this mechanism is known as transactional lock elision. Specifically, we want to focus on the HTM, hardware transactional memory, in this paper. HTM is architectural support for transactional memory, and it's available in various platforms and architectures. HTM exploits cache coherence protocol to detect conflict in programmer-specified code regions. For example, if we look at this update function, programmers can specify where to begin the transaction and where to end the transaction. The HTM will execute transactions in parallel speculatively. And many previous studies show that HTM is capable of lock elision. All right, if HTM is that great, why not replace all locks in Go with HTM? Well, there are several challenges for that. The fundamental reason is the limitation of HTM implementation. Since the hardware resources is limited, it cannot support unlimited track of the transactional regions. Also, there are certain unfriendly instructions to HTM, like syscall or IO. For example, if we have an IO operation in the transactions, and the transactions is guaranteed to abort. Therefore, the performance gain is not guaranteed, and sometimes you can observe huge performance loss. On the other hand, we do have a lot of opportunities. Since the average Go developers are not concurrency experts, and we will have many low-hanging fruits to optimize critical sections in Go programs based on the Mutex lock. All right, in this work, we present our solution named Gocc, which stands for Go Optimistic Concurrency Control. A Gocc is a framework to automatically generate HTM patch for the Go code. Consider the given example input example.go, which has some use of the Mutex lock. The Gocc has an analyzer to tell us which locks should we replace with HTM and which locks we should leave it there untouched. For example, this green region contains a lock, and maybe the analyzer will say, okay, it's a valid candidate, and we can replace that. Then let's look at this region contains the red instruction. We know it's an IO. Okay, then this lock should not be transformed with HTM. Otherwise, the HTM will guarantee to fail. On the other hand, if we have profiles available from the production machines, we can also minimize the code change and focus on the frequently used code. For instance, this orange code, maybe we can say, okay, it's a valid candidate. However, because it's not frequently called, therefore the benefits of using HTM is really limited, and we should just leave it unchanged. After all the analysis, the Gocc will transform the code into a new patch, and the new patch has two new instructions that calls to the efficient and customized runtime library. And there are certain implementation challenges of Gocc. First, we need to automatically identify the lock protected critical sections accurately and efficiently. Second, Go is an interesting language, and it has several quirks. Specifically, we will look at defer in this paper. Defer, as this picture shows, it's a mechanism to delay the function call of an instruction to the end of the function. Let's consider this code example. As we can see, the results depends on if counter is nil or not. Without the defer function, programmers may need to put two unlock in the two different branches. However, with the defer, programmers can call the defer unlock right after the lock acquired. And the Go runtime system will guarantee to release the lock before this function exits. This defer mechanism is really handy to use. However, as you can see, it makes the critical section analysis more complicated. Also, we need to think about function calls carefully, because function calls in some critical sections can call some other functions that include HTM unfriendly instructions. Last but not least, this Gocc needs to cover the nested locks. All right, let's look at how Gocc handles that challenges of lock identification. Gocc used a dominator-based analysis to identify lock and unlock pair, shown in the picture. After that, Gocc will analyze the instructions protected by the critical section and eliminates all the pairs that containing HTM unfriendly instructions. And this approach guarantees the correctness of the transformation. For the more detail, please refer to the paper. Next, let's look at the Gocc runtime contention management. We use the historic HTM success and failure of a critical section to guide the future decisions. And the reason for that is, okay, we want to use HTM only when it's profitable. If we know some critical section has a very high probability to fail, we should stick with lock rather than HTM. We employ a lightweight hash-based perceptron design to implement that. And at a high level, the perceptron takes several input features and combined with the weight, we will take the weighted sum and compare it with a threshold. And then it will tell should we use HTM or not. We also incorporate several techniques from previous HTM studies to avoid performance collapse. All right, let's look at the evaluation setup. We tested on the Intel CPU with RTM for HTM support, and it has 8 cores with 16 threads. And the system has 32 GB memory. The Golang version is 1.15.2. Since Go lacks standard benchmark programs, we just choose some widely used benchmarks like Tali from GitHub. Also, we included other benchmarks based on their popularity from GitHub, like the concurrent stat. This graph shows the performance improvement of GoCC. As we can see, the GoCC can generate significant speed up, and it's also scalable with core numbers, and it has negligible slowdown for the single core case. Similarly, we can see the performance improvement for the concurrent stat benchmarks. And specifically for the len function, LEN, it just returns the length of the concurrent stat, and we can imagine it has a very low probability of memory conflict. That's why HTM works really well. On the other hand, we have programs like clear, which is trying to clear the contents of a concurrent stat in parallel. And we can imagine it has a very high probability of memory conflict. After failing several times, the runtime system, the runtime controller will quickly notice, okay, this has a high probability to fail for HTM, and it will just stick to lock to prevent further performance loss. In conclusion, Go is a concurrency-first language. However, it suffers often due to the lock-based serialization. In this work, we present GoCC to speed up Go concurrent programs using HTM in place of the lock. And the key takeaway here is we change some of the lock sometime. GoCC generates scalable performance with minimum slowdown. It's an end-to-end source-to-source transformer, and it's available on the GitHub. If you have further questions, feel free to send me an email. Thanks for your time, and if you have further questions, please attend the session.